All right, welcome back after a super long break from fluids, or what's called like a super long break, which is good. It's good to have an actual break, even though it was only 2 days. I want to talk a little bit about some of the projects, because I think there's some questions on that. But then we're going to spend today looking, will be kind of a little bit lighter note day, but looking a little bit at turbulence, models of turbulent flow and turbulence, and kind of what they can tell us and how we can use them, and what they can't tell us. What are some of the limitations? So we started last time, if you remember back to what we did last time, we looked at pieces, and we said we have to kind of divide up things into a couple different pieces and parts to be able to deal with them separately. So we had say a pipe like this. Again, at this point, we're just talking about flow inside of an object, internal flow. And we had, so let's say that's R and X. We said if we looked really close to the surface, to the outer surface, if we looked there, what things looked like was we had what we called a viscous sublayer. So we have this thin layer right near the wall where viscosity wins. And when viscosity is winning, we can start to do math to things and actually describe how they work. So we could describe what that looks like. We had U over U star was equal to, make sure I get this right, U star Y over nu, which is rho U star Y over viscosity. So when viscosity is winning, things behave kind of orderly and nice, and we can use math. That works okay at the wall, but as soon as we jump a little bit away from the wall, we have turbulent fluctuations which dominate. And that's where things get tricky. Because now we have, instead of viscosity and kind of nice orderly behavior, we have mixing and randomness, and all of kind of the careful physics that we built up in the Navier-Stokes equation starts to not behave nicely because of all the mixing and the randomness. Like, frankly, we can't handle it in the same way because things are not behaving orderly. To give you, I think it's worthwhile just to have some understanding of where turbulence fits in the broader context of math and science and physics. So I just have a few fun quotes from various people about turbulence and kind of where that fits in the broader context of science. So from Richard Feynman, who likely you've heard at least the name if you don't know who that is, turbulence is the most important unsolved problem of classical physics. So, okay, outside of quantum mechanics, it's about as hard as it gets and as important as it gets. Horace Lamb, I like this one. I'm an old man now, and when I die and go to heaven, there are two matters on which I hope for enlightenment. One is quantum electrodynamics, and the other is turbulent motion of fluids. And about the former, I am rather optimistic. But turbulence is like, there's no hope. Right, Lewis Richardson, this is, big whirls have little whirls which feed on their velocity, and little whirls have lesser whirls, and so on to viscosity. You basically have, and that's a kind of a fun one, because like in turbulence, you have this mixing, and like a big swirl actually will end up breaking apart into little swirls, which break up into littler swirls, and you end up eating away that energy because of friction, because of viscosity. Because when you have these swirling and whirling, you are losing stuff to viscosity. So I like that one. From a little bit more scientific than just quotes by random people. These are a few papers that I found without too much work. They're a little bit old, but I guess such is life. I didn't look very hard. These are two papers published. This one was in 2004, so the relatively recent past. Okay, it was a little while ago, but not that long. This was published in Science, which, if you know anything about scientific journals, Science is one of the two really top journals in all of scientific literature. So it's like Science and Nature. So when you discover alien life on Mars, you publish that in either Science or Nature. Like the stuff about the vaccine for COVID was published in Science. Like this is where you publish the most groundbreaking, the most important scientific results that you have. You publish it in Science. This was published experimental observation of nonlinear traveling waves in turbulent pipe flow. It seems super specific. And it is, but this is just to give you an idea of what the experiment was. They had a pump, which you can see here. That's pumping water, probably, I don't remember what it was, water or glycerol or something, some fluid. They first pump it through a settling chamber, which is basically a chamber that has a whole bunch of probably like drinking straws or something almost exactly like that, which help to use the fluid's viscosity to dampen out any fluctuations or any movement like that. So you get all of the fluctuating part gone as much as you can. And then they pump it through this 4-centimeter diameter pipe, and they have a disturbance generator here. So basically what they're doing is then we can put into the fluid, we have all of the disturbances as much as we can gone, and we give it some disturbance and then kind of watch what happens. And we want to see, like, can we predict and can we model what's going to happen when we give some artificial disturbance? What they found, this top, these are all at different Reynolds numbers. The top, this is their experimental data for how these disturbances are propagating in the pipe. And this is some of their modeling. So the reason a paper like this ends up in Science is because we're starting to get some actual like physical insight into how these disturbances are propagating. You can see there's not even perfect correlation between the model and what's actually happening, but it's pretty good. You can actually see some of the same types of features, say, in those two. You can see a lot of the same features from their model are actually representing what's happening in real life. I don't know, to you, it seems, to me, it seems like this is the stuff that's like considered like really at the cutting edge of scientific research, is understanding, like, we bumped a fluid a little bit and watched what happened. I don't know, it's kind of interesting. Here's another one. This is more recent. This is from 2011. Also in Science, the onset of turbulence in pipe flow. So what they're looking at is probably a very similar experimental setup. And what they have is essentially they're, again, doing the same thing. They're kind of getting all of the fluctuations out, and they're adding a single disturbance, and they're kind of watching how that initial disturbance ends up cascading into the next disturbance and the next disturbance. So they're, again, doing kind of a mix of simulation. So this, some here in A and B, this kind of branching stuff is some simulation that they're then using to match that back into what their experiments are showing. And this is really how we handle turbulence. Predicting turbulence from the ground up is essentially impossible. But what we can do is we can look at experiments and use that to inform our models and kind of use that as a feedback and start to get some information about how turbulence works from this kind of synergy between experiments and modeling. There's a lot of, it seems like kind of a trivial thing. Maybe it does to you. It's not though. When you think about like how important fluids moving are to like weather prediction, designing the like a system for looking at drug delivery in your blood, designing something for say like a pumping system or piping system for like a municipal water supply. Whether exactly how all of these things work in a very wide range of fields has a lot of different consequences. So looking at how turbulence works, turbulent flows are all over the place. And getting some better understanding at how we can think about them, how we can model them, what's kind of happening in this transition region where we're a little like kind of at the border between laminar and turbulent is a lot of where research, like kind of cutting edge scientific research in fluids, that's where a lot of that is occurring, looking at turbulent flows. You kind of have two areas that like if you were to do research in fluid mechanics, you'd be looking probably either at turbulence or you'd be looking at non-Newtonian fluids, like fluids that aren't perfect, like quote unquote perfect fluids. And there's a lot happening in both of those areas, but that's kind of where the cutting edge research part of fluids is today. We're not obviously going to go through that in any more detail than just kind of looking at some figures and saying, huh, kind of interesting. But what we are going to do is look today a little bit at how we can develop models of fluid flow, which are useful to help us do things that we want to do. So how can we develop models that help us then make predictions about how systems are going to behave? So we already talked a little bit about what we can do, say to handle what's happening in the viscous sublayer and how that's behaving and how that's working and what we can, how we can model that. The other thing that we can do is we've looked at just from a kind of more of like free body diagram, looking at fluids, we've developed like looking at the shear stress. So this is something we wrote down last week, du dy minus rho u prime v prime bar. If you remember, we wrote this last week. This is what the shear stress looks like in fluids. It's made up of two parts. So this is from viscosity this part is from turbulent mixing, from the swirling and whirling and viscosity that comes along with that. Obviously, if what shear stress is like layers of fluids sliding past each other and there being friction for that, when you have fluids swirling and mixing like that, there's a whole lot of that type of shear stress going on. So when we're at the wall, viscosity is the most important part. When we're a little ways away from the wall, then all of a sudden the mixing wins. So we can see a little bit of what that looks like. If we look at some experiments looking at shear stress, so we predicted is max at the wall, 0 at the center, and varies linearly. So you don't need to remember all of these individual points, but we a little ways, I think, I can't remember if it was Monday or Wednesday of last week, so it was a little bit ago. But we predicted that tau should vary linearly with radius, where it's 0 at the center, there's no shear stress at the center, again, on average, and it's maximum at the wall. So here's some experimental data that our book has. And let's just point out a few kind of interesting points from this. So what we are predicting is that shear stress should be a max at the wall. So 1 is the maximum, and it should be 0 at the center. So it should be a line like that. Okay, close. A line like, that's bad. Like that, close enough. So this is the total shear stress. These dots are the turbulent shear. Again, measured from experiment. The squares are at 500,000 Reynolds number. The circles are at 50,000 Reynolds number. Both, right, our cutoff is like 2,300. So both are a lot bigger than that. So it's definitely turbulent flow. So this says that you can see, I mean, basically all of the shear stress is from this turbulent mixing. So this is only, like the dots are only the turbulent mixing part. All of the shear stress is essentially from that turbulent mixing everywhere up to like 10% of the way away from the wall. So that's what this this x-axis is. It's the percentage away from the wall. So this is the wall. This is the center. And you're saying like here we're 20%, here we're 40%, 60%, 80% of the way to the center. This would go then like it would drop off so that the turbulent part is 0 actually at the wall. And then there would be a second component that's from viscosity that kind of looks like that. So this would be like viscosity only matters in that like little teeny tiny region right at the surface. And everywhere else, it's the mixing and swirling. That's the important part. Okay, another way to look at that. This is one model of fluid flow. And looking at kind of, again, so these are experimental data. The solid points are the center of the system. So this point here, that's the center. This point here, that's the center. So those are the center of the pipe. The circles are one experiment. The squares are a different experiment at a different Reynolds number. What we see, the y-axis, this is like a non-dimensional length. Y u star over nu. Right, you may recognize it from this equation. This is the x-axis on a log scale. So a straight line on a log scale looks like this. So this is our model here. This is the model that we derived ourselves for what's happening right at the wall. And we can see this fits, like the wall is at 0, but it's a log scale, so we can't get to 0. So this is basically, think of like that's the wall. If we're really close to the wall, that model fits super well. So we can derive these kind of models from first principles and describe what's happening at the wall. But this model very quickly, as we move away from the wall, breaks down and starts to give us garbage. So this would predict like it goes like that, which obviously the data shows it doesn't do that at all. So this model works, but it only works in this very specific context of like right next to the wall's surface. It only works when the wall is there to like dampen out any of the mixing because of the no slip condition. So it works in some places, it doesn't work at all in other places. Then for the part where we have mixing and swirling and whirling and all of those fun things, essentially what we have to do is look at the data, kind of squint our eyes and slap a model on it. Right, we do this in engineering quite a bit. We say, well, that looks like it's sort of linear on a log X plot. Right, you can convince yourself like these data points are pretty close to linear. So we'll just slap a line on it and call it good, right? And here's the line. It just has some unknown constants and it doesn't fit perfectly. It fits kind of okay through most of the system, but at the center, we start to deviate a little bit. Here too, at the center, we start to deviate a little bit from that, but it's close. And that's essentially how we're going to be modeling turbulent flow. Is in regions where like the turbulent part of it dampens out, we can model it and actually get like first principles, you know, starting from Navier-Stokes, we can do force balances and we can derive up our models kind of from the ground up. In the random part of things, we have to take data and kind of squint a little bit and slap a model on top of that data. We're not doing the same like, let's derive our models from the ground up and be able to build them from the ground up. We're looking at it and kind of waving our hands and trying to fit an equation to what the experiments are showing us. So we have two kind of fundamental differences in how we're building our models for different parts of this, and a really big difference between how we're building models for laminar flow and how we're building models for turbulent flow. In laminar flow, it's easy. We take the Navier-Stokes equation and we can solve it and we have everything that we need to know. Like from the ground up, from force balances and stuff. We get all of a full description of what's happening. For turbulent flow, we are doing kind of the exact opposite. We're taking an experiment, we're kind of fitting a model, it doesn't fit great, it fits okay, and it kind of gets us to a point where like, okay, we can use that. But it's like, it kind of fundamentally flips how we have to think about the problems. Okay. This is one equation or one model for turbulent flow. Now we can discard that, go back to here. So let's look again and just write a few notes down before we look at the next model. So away from walls or surfaces, U prime, B prime, remember those are the random fluctuations. Those win, those become the dominant factor, and that is why we have such a hard time dealing with it. So we look at experiments and fit models to data. We're kind of completely changing. We can't predict things from the ground up in the same way that we can with laminar flow. With laminar flow, I can go and like take something that's never been looked at before. Like you have no idea what's happening. And if it's laminar, I can build from the ground up what's going to happen and make predictions about how it's going to behave and be right about that. It like totally is different. For turbulent flow, you can do some of that, but you end up, a lot of it has to be, you have to run it through experiment. kind of in addition to, or at least like compare it to other people's experiments. You have to have models that are based in some form or fashion on experiment. So, so we looked at one model showing, okay, this is one that we won't really use that much in practice. But just to show, like, the model that we will use a lot is not the only game in town, because all of this is like fitting an empirical model to data. So this is the one model that we just looked at. 2.5 times the natural log of y u star over nu plus 5.0. So like, what's special about 2.5 and 5.0? Absolutely nothing. They just are constants that are there because we fit the thing to a line. So they don't have physical significance. They're just numbers from fitting. The model that we'll use most often is called the power law. Is that right? Again, this is an approximation based on an experiment. With this model, it's going to be the same kind of form. This is max velocity, right? U bar is the average velocity. So we're always stuck dealing in averages. This is equal to 1 minus r over big R to the 1 over n, where n is a constant. Usually maybe something like 6 to 10. It's a constant. It changes depending on, well, let's look at the data. So this is the model that we'll most often use to be making predictions, at least in this class. But like I said, this is another acceptable model that we could also use to make some of these same types of predictions. And neither one is true. They're both just possibly useful. Okay, let's look at that. Let me look at, okay, I guess I killed it. All right, so this is one model. Here's our the power law approximation. This is what that says. Again, just to describe a little bit of what we're looking at. This is the distance from the, like down here is the wall. Up there is the center. It's a normalized distance away from the wall. And this is a normalized velocity. This is like max velocity. So the maximum is at the center. So we should go, like at the center, we should be right there. So this fits, these are again at two different Reynolds numbers at 5 times 10 to the negative 4, 5 times 10 to the negative 5. The power law model fits reasonably well kind of all through this region, right? But if we were to extrapolate it out, it would predict us going like that, where our actual data goes off in this direction. So in certain regions, it works great. In other regions, it works like it would predict crazy things happening. It would predict that we're still like 20% of our max velocity, like right at the wall surface, when in reality, we're pretty much stopped at that point. So it works okay where it works okay, and it works really bad in other places. So you have to know, which this is totally different than when we were doing laminar flow models. A laminar flow model, we can get a model built from the ground up. We can ask it any question that we want, and it will give us the answer. For turbulent flow, we have to make sure we're asking the right question to the right model, because none of them work everywhere. So it becomes a little bit of a different game. We have to make sure like we have calibrated what question are we trying to ask, and then like what is the appropriate model to ask that question. And we don't have like a one size fits all thing like we do in laminar flow. We're going to have like empirical models and correlations and tables and a lot more of that type of stuff that are specifically designed for like this one situation rather than a one size fits all thing like laminar. Okay, this is just to show you on the right is the, like, what does the shape look like? So again, this is the wall here. This is the center. So it would, right, you would kind of mirror image all of those onto the other side to get a picture of like the whole shape. This is laminar flow just for kind of your eye. So it would be, right, that parabola. That would be the velocity profile. We would draw it like this. Okay, right, we've drawn that a whole bunch. Turbulent flow, this is, again, this isn't exactly what it looks like, but this is what the power law model looks like, which is good in some places and bad in other places. The power law model looks like this. So it's really a lot flatter. That's kind of a bad one. So it's going, okay. And so it looks, remember we used, when we were doing Reynolds transport theorem things like calculating forces, we said, let's assume a uniform velocity because that makes our lives easier. Turns out, if we're in turbulent flow, uniform velocity is not all bad. Right? If we're in laminar flow, like this one is clearly not, the laminar is clearly not uniform. But turbulent flow, it actually is fairly uniform. And that's because any of the fast moving fluid in the center gets like mixed in with the slow moving fluid near the wall. Like they can just swap places. So when they swap places, like fast fluid goes out to the wall because it got swirled there in like a vortex, and slow fluid gets swirled out into the center of the pipe. So it all gets swirled and mixed together. So these fluctuations basically flatten out your velocity profile. So throughout most of the center of the pipe, we're pretty uniform. Once we get close to the wall, okay, then things are different. But throughout like a majority of the pipe, right, kind of from there to there, we're like pretty much at the maximum velocity, pretty much at the same velocity everywhere. But we could use a model like the power law model to get maybe better descriptions where we don't have to assume just uniform velocity. Like we can actually say, well, let's assume it looks like this, and then we can use that. Let's look at, okay, let's get back to our notes a second. So the power law model, this is a useful model of turbulent flow in a pipe. It is not a true model of turbulent flow in a pipe. It's not true, but it's useful. So when is it useful? Let's ask some questions. Is this model true? No, but we're not always interested in engineering if something is like fundamentally true or not. We would like it to be. If you can get at like the kind of base fundamental truth and describe reality kind of from the ground up, like that's great. We like that, but we have to design things even when we can't do that, even when we have turbulent flow that we can't describe. So let's look a little bit at the limitations of this. So it's fairly good. But let's ask it kind of a simple question. Let's ask the model a simple question. What happens at the center? What should happen at the center? Well, at the center, we should see, like, that's our maximum velocity, right? Okay, so we should have our maximum velocity at the center. Is that the case? Yes, that's the case. Okay, what else should happen at the center? At the center, we should see, like, that's a maximum, so that should mean the derivative is 0. We should see du dr evaluated r equals 0. That should be 0. We should have a nice, like, clean curve that gives us a nice maximum right at the center. The shear stress is 0. We get the derivative is 0. That should be the case. That's the case for our laminar flow models. They would predict that and be happy and everything would be great. This is true in real life. But our model predicts would be dr of u bar, which is capital U 1 minus r over big R to the 1 over n, evaluated at r equals 0. You can do this if you want at home, or you can just trust me that that doesn't equal 0. So we could take the derivative, we could evaluate it at 0. It should be equal to 0, it's not. So even asking it a basic question like, do you accurately model what's happening at the center? The answer is no. What happens at the walls? Well, what should happen at the walls? Well, at the walls, there should be some shear stress, right? I don't know how much, but it should be there. It should be some, it should be a number. There's some finite amount of shear stress at the walls. So D evaluated at R equals big R should I guess that would be mu times that, should give the shear stress at the wall. That's just like a number to give us a value. What happens when we do that? We get du or dr capital U 1 minus r over big R. Again, I'm not going to do this in any detail, but if we were to take that derivative and evaluate it at r equal big R, this equals infinity. So it predicts that there's an infinite amount of friction at the walls. Obviously, that's not true. So you can get things that are like totally nonsensical and non-physical if you ask the wrong question to the wrong model. And that's kind of a key difference between all of the stuff that we talked about with laminar flow and all of the stuff that we're going to talk about with turbulent flow. Because we can't model it, our models are like fine-tuned to answer a specific question. And if you ask the wrong question to the wrong model, you get something dumb. You get something like friction's infinite. Like friction's not infinite. It's a thing. It's a number. It can't be infinite, but that's because you asked this model, which isn't real, but is designed to be a tool for answering a different question. So for this specific model, okay, it fails on these two counts. What does it do relatively well? We can use it to look at the mass flow rate in our pipe. So we did this with laminar flow. We took the velocity profile and we integrated it to get the mass flow rate. You remember doing that? We could do a similar thing with this model and get the same types of answers. We could get good answers. So we could figure out mass flow rate. We could figure out momentum. So instead of falling back on, so if we had something with laminar flow, we know the velocity profile and we can do our integral from the center, right? Remember Reynolds transport theorem? Most of the time we said, well, let's assume a uniform velocity, then we don't have to do the integral. We could use a model like this to be able to kind of get more sophisticated than what we were doing before. And we could figure out what is the momentum given the velocity profile. We get a fairly accurate answer. The last thing that we could find, and this is what we'll mostly do, this is kind of the next question that we're going to ask. We could look at the kinetic energy, because really the next step for us in the class is looking at energy and energy in fluids and how does that work and change. So if we wanted to look at kinetic energy, right, again, we've done this with laminar flow. You did a homework problem where you looked at what's the kinetic energy of the fluid given a laminar velocity profile. But if we had turbulent flow, we could use something like the power law model and do some of the same things. The math would be different, but the process is exactly the same. That would give us a relatively good approximation at what the kinetic energy is. So all of these models are tuned for specific questions and they work okay for that, but they sometimes give out garbage for a different question that you might ask it. So you have to make sure you've kind of asked the right question to the right, you know what question you care about, like what are you trying to ask, and then which model should I be asking. The last point, so I think we didn't say this. So if you go back a little bit in your notes, I'm just realizing I didn't say this. This value n, so like the 1 over n part, just to look, right? So if n is 10, that means we're like really flat. So that's this guy, n equals 10. If it's n equals 6, that's this other guy a little bit less flat. The n value that you're going to choose, that's based on the Reynolds number. So essentially, for this class, we're not going to get too picky. We'll probably just like pick a value, 7 or 8 or something like that. But as the Reynolds number goes up, n goes up. So if you have a Reynolds number of 10 million, then n is maybe going to be 10. If you have a Reynolds number of 3,000, n is maybe going to be about 6. So it'll be somewhere in that 6 to 10 range. But you can see even from this picture, there's not a huge difference. So all turbulent flows are going to be pretty flat velocity profiles. throughout the whole center section of the pipe. It's going to be the fastest at the middle, but it's going to be, even pretty close to the wall, you'll still be like 80% of the max velocity. So it's fairly kind of flat nosed, but it's going to be more flat the more turbulence, the more mixing that there is. Okay, so we are going to be jumping really in kind of more detail next time into energy and pipe flow, but I just want to define two terms. So if you remember, we'll call this energy considerations, just to define terms that we'll dig into a little bit more next time. Bernoulli is so far what we've used for energy. Bernoulli is frictionless flow, but friction matters in a lot of real life settings. Sometimes it matters a ton. So we need to build friction, and talking about friction, thinking about friction back into the system. So that's where we're kind of headed, is how do we do some of the same kinds of things as Bernoulli, but add friction back in. Bernoulli would say that like pressure plus rho V squared over 2 plus rho GH is a constant, right? This is our mechanical energy balance. So it says mechanical energy is conserved, and that's true kind of as far as it goes. But if you have friction, that's going to take some of your mechanical energy and convert it to heat. So we're going to have to figure out, okay, how can we handle that? So that's kind of where we're headed. But before we do that, we'll talk just the last minute, I guess, 3 minutes. Two ways that we're going to use to talk about that, and these are things that you may see elsewhere, kind of depending on where you encounter fluids, you'll see different terms come up. If you divide Bernoulli by like rho g, you have P over rho g plus V squared over 2G plus H equals 8 capital H or EGL. H is the total head, so these are both the same. H and EGL are the same thing. The total head, EGL is the energy. Grade line. Both of these are, that's the worst little bracket. Looking at total mechanical energy of a fluid. So you'll find these when you, in a lot of places, you'll talk about the head. It's like, how much total energy do I have available? Mechanical energy do I have available? Pressure, kinetic energy, viscosity, or kinetic energy and potential energy. What's the total amount available? That either is talked about as the head or the EGL. It has, both of these have units of length slash height, like feet or meters. So you can talk about what's the total kinetic or the total mechanical energy. It's like 50 feet. And that would be, or what's the total head? 450 feet. The other way that we can talk about it, and we'll define these a little bit better next time, is just looking at called the hydraulic grade line. or the HGL, which is equal to P over rho G plus H. So it's basically equal to the same thing, but not the velocity part of it, which again is a thing in feet or meters. We'll talk about both EGL and HGL and why we care and how we measure them. But more importantly, we'll talk next time about friction and how we can build friction into some of these models, discuss losses, and more of like a full like first law of thermodynamics picture of energy and fluid flow. So that's what we're building toward next time. So yeah, come back Friday and we'll talk first law of thermo. Have a good Wednesday. Enjoy the beautiful sunshine.
Thank you.
So we are working.